Hello everyone, and welcome. Chillo, today we are going to start a very important topic from our first unit, electric charges and fields. The topic is the electric dipole. Now, I know it might sound a bit complicated, but don't you worry at all. We're going to break this down so simply that you'll not only understand it perfectly, but also know exactly what to write in your exams to get full marks. Let's begin.
But before we dive into the definitions, let me ask you a question, something you've probably seen every day. You put your food in a microwave, and it gets piping hot in just 2 minutes, right? But the plate it's on, it's often still cool enough to touch. Have you ever wondered why? What's the physics behind this?
Well, the secret isn't some kind of magic, it's pure physics. And it's all because of these tiny things called electric dipoles that are present in the water molecules inside your food. So you see, this topic isn't just for exams, it's happening in your kitchen right now. To understand how a microwave works, we have to first understand what an electric dipole really is.
So, let's get to the main question then. What is an electric dipole? Let's break it down into the simplest possible idea.
Okay, let's forget physics for a second. Just imagine a tiny team of 2 partners. One partner is completely positive, and the other one is completely negative. Now the special thing is, their strengths are exactly equal, but their natures are completely opposite. And they are always found together, stuck a very small distance apart. They are a pair, a package deal.
And this is how we draw that tiny team in our physics notebooks. See, we have a negative charge, which we call minus Q, and a positive charge, plus Q. Their values are the same, but their signs are opposite. And they are separated by a small distance that we label 2a. This whole system, this pair, this is what we call an electric dipole. Simple, no?
And now for the most important part, what you have to write in the exam. This is the definition, word for word, from your NCERT textbook. It says, an electric dipole is a pair of equal and opposite point charges, Q and negative Q, separated by a distance 2a. It's exactly what we just discussed, perfect and precise.
Okay, so now we have this dipole system. But how strong is it? How do we measure its effect? Just like we measure force in newtons, we need a way to measure the strength of a dipole. And for that, we use a very special physical quantity. This quantity is called the electric dipole moment. We use the symbol P for it, and listen carefully, it's a vector quantity, which means it has both a value, a magnitude, and a direction. Calculating its magnitude is super easy. It's just the value of one of the charges, Q, multiplied by the total distance between them, which is 2a.
Now, since it's a vector, we need to know its direction. This is a very crucial point. By convention, physicists all over the world have agreed that the direction of the dipole moment vector P is always from the negative charge towards the positive charge. Please remember this, from minus Q to plus Q.
All right, we know what a dipole is, and we know how to measure its moment. Now the main job of any charge system is to create an electric field around it. So, let's figure out the electric field produced by our dipole. This is a very important derivation for your board exams.
We usually calculate this field at 2 standard locations. The first is on the axis of the dipole, the line that passes straight through both charges, and the second location is on the equatorial line, which is basically the perpendicular bisector of the line connecting the 2 charges.
So let's start with the axis. How do we find the field there? We'll just use our good old principle of superposition. It's a simple 3-step process. First, find the electric field at that point because of only the positive charge. Then, find the field at the same point because of only the negative charge. And finally, just add these 2 fields up like vectors to get the final net field. Now, after we do the vector addition and apply a small approximation for points that are very far away from the dipole, where the distance r is much bigger than the separation a, we get this nice clean result. The electric field on the axis is about 2p divided by 4 pi epsilon naught r cubed. The key thing to notice here, the field depends on 1 over r cubed. It falls off much faster than the field of a single point charge, which was 1 over r squared. Now, what about the equatorial line? Well, the logic is the same. We calculate the field from plus q and minus q. But look, because of the beautiful symmetry of the situation, the vertical components of the 2 electric fields will perfectly cancel each other out. So all we need to do is add up the horizontal components to get the net field. So when we add those horizontal components, and again use the far field approximation, this is the final result we get. The electric field is approximately minus p divided by 4 pi epsilon naught r cubed. Once again, notice the 1 by r cubed relationship. And that minus sign is very important.
It tells us that the net electric field on the equatorial line points in the direction opposite to the dipole moment vector P.
Okay, now for a section that I call the Mark Saver section. Let's talk about the common traps, the small, silent killer mistakes that so many students make in exams, and how you can avoid them.
First trap. We all know the formula for dipole moment is P equals Q times distance. But my question to you is, what exactly is that distance?
This is a classic trap. So many students, in a hurry during the exam, just write A as the distance. And that's wrong. Please remember, the definition and the formula use 2A, which represents the total distance between the plus Q and minus Q charges. Always use the full separation.
And the second big confusion is about direction. That dipole moment vector, P, does it point from positive to negative or from negative to positive? It's easy to get confused. So let's make it crystal clear. You must remember this for life. The dipole moment vector P always points from the negative charge to the positive charge. A good trick to remember this? Just think about a normal electric field line from a single positive charge. It points outwards, away from the positive, right? The dipole moment is the opposite of that convention. It goes from negative towards positive.
Excellent work. We've covered the concept, the main formulas, and also the common traps. So before we wrap this up, let's do a quick 1-minute revision of the most important points.
So what are the key takeaways? First, a dipole is simply a pair of equal and opposite charges, plus Q and minus Q, separated by a distance 2A. Second, its strength is measured by the dipole moment, P. It's a vector that points from negative to positive, and its value is Q times 2A. Third and fourth, you must remember the final formulas for the electric field at far points. On the axis, it's proportional to 2P, and on the equator, it's proportional to minus P. And finally, the most unique feature, a dipole's electric field falls off as 1 over r cubed, which is much faster than a single point charge.
So, now we understand a dipole and the field that it creates by itself. But an interesting question comes up. What happens if we take this tiny dipole team and put it in someone else's electric field, an external field? What kind of forces will it experience? Will it start to rotate? Well, that's exactly what we're going to explore in our next explainer. I'll see you then.